Hello and welcome back from Thanksgiving break. I am sorry that I can't be with you today in person, but I'm thankful for a wonderful sub and technology so that we can still learn together virtually by this video. So I will ask that you put away phones just as you would in class, even though maybe I'm not around to put it in the cubby for you, that you can show the maturity and self-control to put that away and limit your distractions. I will be going through some problems and you will take notes on your own paper with me. There will be an assignment following this set of notes. Let's begin. The first section of notes is going to cover simplifying square roots. So this is technically review. So I will do just a couple of examples to review this with you. Example 1 is asking us to simplify the square root of 28. Please write this down. Notice that the calculators are gone for many reasons. One, because I'm missing too many, but also because we will not be using calculators in this section. You'll see why in subsequent lessons, but it's super obvious here that a calculator would do all of the thinking for us. So we're thinking about how we can simplify square roots by looking to see if there are any perfect square factors, which means by making a factor tree. So that is the work that I expect you to show here and on all of the problems to follow. All right, so let's make a factor tree. To do so, you can come up with whichever factors you think of first. So there doesn't necessarily have to be one right way to get the problem started. For 28, I think of 4 times 7, and then 4 is my perfect square, right? So if there is a factor that is a perfect square, then we know this square root will break down because 4 is 2 times 2. So I would break down the square root of 4 as 2, and then I don't know the square root of 7, so that stays inside of the square root. So back in Algebra 1, or even when we reviewed this last chapter, I call this the pairs and spares idea, right? It's cute because it rhymes, but pairs means if I have a pair of factors, then I can factor those outside of the square root. And yes, we did review this quite briefly when we saw the quadratic formula, but usually we just let the calculator do it for us. Here I want to drive home the concepts because again, we're going to build on this later in the week, so we need to understand the concept behind breaking down a square root. Again, there's no one right way to do the problem, so if you had done 28 as 2 times 14, and then you broke down 14 as 2 times 7, notice we're still going to get the same answer. So we'll show work, and that work doesn't necessarily have to look the same as your partner's. Let's try another. The square root of 80. So whatever you see first, we're going to try to break it down. Perhaps numbers that end in a 0, you see a 10 as a factor. So we did 8 times 10. 8 I could break down into 4 times 2, and 4 I know is a perfect square, so I can do 2 times 2. But we're not done, right? Let me cross out what I have broken down so I don't get confused in all my work that I'm showing. The 10 also would break down to 2 times 5, so in this case there's 2 pairs of 2's. So 2 times 2, or 4, would go out of the radical, and 5 would stay in. What that really means is if you were looking for a more efficient way, then maybe you saw 80 as 5 times 16, and then you just saw 16 as your largest perfect square to take out the 4, leaving the 5. I didn't necessarily see that from the get-go, so instead I just broke down all the way into the 5 prime factors. All right. So speaking of efficiency, as the numbers get bigger, sometimes we do want to look for more efficient routes. So something like the square root of 200, yeah, we could do lots of options. We could do 20 times 10. We could think about quarters and break that up into 8 times 25. But the most efficient way is to look for the largest perfect square factor. So 200 is 2 times 100. 100 being a perfect square means I could factor that into 10 times 10, right? So the 100 will break down, the square root of 100 is just 10, the square root of 2 we don't know, so that would stay inside of our radical. So that's the most efficient way, is to look for the largest perfect square. All right, one final one on this topic. If there's a number out in front, that number is just a coefficient, right? So just like I could write negative 3x, that means negative 3 times x. Well, negative 3 times the square root of 24, that is just a coefficient that's going to multiply my answer after I simplify it. So I'm going to break down the square root of 24 like normal. So I see that as 4 times 6, and 4 again is my perfect square. So 4 is 2 times 2. 6 technically breaks down, right? But it just breaks down into 2 times 3, so it doesn't break down to any other perfect square factors or any other pairs. Remember, if we're thinking pairs and pairs. So really that 2 times 3, or that 6, is going to stay inside of the radical. What I'm bringing outside is a 2, but then this is where 2 would really get multiplied by the negative 3 coefficient that was outside the radical. So I'll have a negative 6 on the outside and square root of 6 on the inside. Okay? So don't worry about a coefficient until the very end, and we'll just multiply that by whatever comes out of our radical when we simplify. So there's the first topic of the day. Went through pretty quickly because I do know it is review, and even something we kind of reviewed this year, but again, we did so with a heavy reliance on a calculator, that we will have to do this quiz, all of this next quiz, without a calculator. So making sure we know our factors, building a factor tree could simplify square roots. Another potentially review, but maybe you don't remember this as much, is the idea of graphing square root functions. So we've talked about all sorts of functions this year, starting with our basic linear functions. We just wrapped up a unit focused on quadratic functions, and each family of function makes its own shape on a graph. Well, we're going to see what a square root function looks like, starting with the most basic square root. So write down y equals the square root of x, and we'll call this our parent function, right? Because this is the simplest square root problem where we have the square root of x. Now, just like with quadratics, I can't stress enough, although it feels elementary, that making a table is always what we could do when we're trying to explore a new function. So we're going to make a table, we're going to graph. I understand you're doing this on your own paper, so it doesn't have to look perfect, but we just want to know generally how to make the table and then recognize at least what the graph will look like. And on the assignment, I will print the graphs for you. Okay, so let's make a table. But what we have to think about here is what numbers to put in our table. So for example, with quadratic functions, we were really thoughtful and we always put the vertex in the middle of our table. But really we said the domain was negative infinity to infinity. So really we could have put any x's that we want. We don't have that luxury here. Because notice, I'm square rooting an x. And what we've established this year is that when we square root a negative number, we get imaginary. Well, I can't graph imaginary numbers, so imaginary numbers aren't going to pop up here if I'm trying to graph on the real xy coordinate plane. So instead, I'm trying to think of, okay, I can't use negatives, so what numbers can I use for x? Well, I could definitely use 0, right? If I plug that into the function for x and find y, well, the square root of 0 is 0. So 0 is the first number that actually works that I can plug into this function. I can plug in 1. And then the square root of 1 is just 1. We're thinking, okay, this is looking linear. But here's where it starts to get more tricky. I could technically plug in 2. But what is the square root of 2? I don't know, 1 point something. It's not pretty, so it's not going to be easy to graph. And I just said we can't use a calculator. So although 2 is possible, it's part of our domain, it's not a good number that I'm going to actually want to use when it comes to making a t-table. So what's a good number is going to be perfect squares. Okay? So my goal is to plug in perfect squares, yikes, turn that around a little bit, for x. So the next perfect square I could plug in is 4. Right? So then I could do y equals the square root of 4, and then I know that the square root of 4 is 2. So 4, 2 would be up here. And now we can start to see that this isn't linear. Those points are not just in a straight line. Again, graphing by hand maybe isn't the easiest, so let's do one more point. So let's do the next perfect square. So 5, 6, 7, 8, those are possible, but I don't know the square roots of those. So I'm going to jump to 9. And the square root of 9 I know is 3. So notice I'd extend my graph out to 9. I'm up here at 3. So this graph curves. It is not straight. And it started at the origin. So that makes the domain from left to right. It started at 0. And then I could go forever, forever to the right. It also started at 0, started at the origin, and then goes up and up forever. Pretty gradual, but it goes to positive infinity for both the domain and range. So this is our parent function, our simplest square root function. And since the numbers do get pretty large pretty quickly for our x's, we can just make a table of 4 values each time to graph those. So let's do a couple more. All right, so I just said we can make a table of just 4 values this time so that they'll fit on our graph. And again, I want to think about what numbers actually make sense to plug in here and take the square root of. Well, those numbers are going to be perfect squares. They also can't be negative. So 0 is a perfect square, 1 is a perfect square. Then I'm going to jump to 4 and then jump all the way to 9. Just because those are the x's that will give me pretty answers, right? Numbers that'll be easy to graph. And then we just plug those into our function. So what is the square root of 0? Still 0, but then plus 2. And the square root of 1 is still 1, plus 2. And the square root of 4 is 2, and 2 plus 2 is 4. And the square root of 9 is 3, and 3 plus 2 is 5. So when it comes to graphing, and you might see on your assignment tonight, the graphs aren't always just centered at the origin. I can really focus more on the right side of the graph and just kind of sketch this to the best of my ability. So 0, 2, 1, 3, 4, 4, 5, 6, 7, 8, 9, over 9, up 5. So it's that same curved shape, right? And notice the arrows are not on both ends. It has a starting point, and at this case, the domain is 0. So on the left, it starts at 0 and goes forever to the right. And up and down, it starts at 2 and then goes forever up, up, up. So this point, 0, 2, is my starting point. Notice there's no arrow here. This is where the graph starts. So I'll see that in my domain and range, and I should see that because it's the first value in our table. All right. Can only record a 15-minute video, so I'm going to give you a second to pause and try this one. All right, I trust that you tried this, so let's kind of finish it up quickly. Again, if 0, 1, 4, and 9 are the numbers to plug in, then I would take negative 3 times the square root of 0 and still get 0. Negative 3 times the square root of 1 and get negative 3. Negative 3 times the square root of 4. So negative 3 times 2 is negative 6. Graph isn't perfect, but good enough. Negative 3 times the square root of 9. So negative 3 times 3 is negative 9. 5, 6, 7, 8, 9. So something like this, where I still have that same curve shape, but opening down. So that effect, my domain is still 0 to the right forever. So 0 to infinity. My range, though, think about how it opens down and then actually stops at 0.